So this was a directional derivative problem, but it was a multivariable function of 3 variables, right? So what we've been primarily doing is what directional derivative and functions, 2 variable multivariable functions, right? So it's like we had our surface z as a function of x and y. That lives in R3, right? It's a surface in R3, and then in terms of direction, the direction for the directional derivative was an R2 phenomenon, right? Our unit vector was, was an R2 vector that determined the direction that we're interested in the directional derivative. So now we take that situation and we look at this thing in this whole situation in R3. So in R3, what is this? So this is our function now. It's a function of 3 variables, right? So where does that live? Where does a multivariable function of 3 variables live? Anybody? Is this blinking? I keep seeing it blinking. Is it blinking? Yes. Oh, okay. All right. I'm not going crazy. All right, let's just hope it gets better. All right. Oh. Or worse. Let's try this. Okay. So multivariable functions of 2 variables, they graph as surfaces in R3. So what would a multivariable function of 3 variables graph as? What's that? Okay, so yeah, so that would be something it's kind of like, it's called a hypersurface that would live in R4. But that's so there are ways to render that. So we live in a 3-dimensional world and we work on a 2-dimensional drawing surface, right? So there are ways to render these, but they're just not very convenient or friendly, right? So it takes some imagination to do that, okay? But then what about the direction? So this is where that function lives, but then in terms of the direction for the directional derivative, what about that? So here, our surface, our multivariable function, the surface lives in R3, and then what about the direction that we pick? The direction that we pick is R2, right? It's a vector in R2. It's a vector in the xy plane. That determines direction. And then we use the directional derivative to say what the rate of change is on the surface, right? So if we step it up 1 dimension, then we've got a surface in R4, and our direction is in R3. So we can manage that, right? So we can think about that's easy because so we just in R3 it's like at the point 1, -4, -5. It's down here. So 1, -4, -5. So that's our what? That's our value of the independent, right? We're going to put 3 values in, and that's our independent quantity. It's the combination of three values of 3 variables. And then the function's going to spit out like a w, like a 4th variable, right? But we can think about the direction that we're going to, so we can go in any direction in R3 from that point, and then the directional derivative will give us the rate of change in that direction, the rate of change of this 4th variable, right? The rate of change of the 4th variable with respect to going in any direction in R3 from that point. Does this make sense? Is this making sense? So it's all analogous to what we did, but stepping it up 1 dimension, okay? So by stepping it up 1 dimension, now our direction, rather than a direction being an R2 vector, it's a direction in R3. So what direction do they want here? They want in the direction of the origin. In the direction of the origin. So what's the direction of the origin from the point 1, -4, -5? Just the direction first. So what's the direction of the origin from the point 1, -4, -5? It's going to be -1, 4, 5, right? So the position vector 1, -4, -5 would be from the origin to the point. So take the opposite of it, and you'd have the vector from the point to the origin. But if we're going to do the directional derivative, is this u? What's u then? We got the right direction, but what are we going to use to find the directional derivative? We need unit vector in that direction, right? So our u is going to be -1, 4, 5, but then each of those over, I think, square root of 42, 16 and 25 and 1. Is that 42? And then what are we going to do to get the rate of change in that direction? Partial derivatives to get the gradient, but now your gradient vector will be an R3 vector, right? Your gradient vector will be R3. So what is that? The gradient of f will be -4x, 2y, and 10z. And then we want that evaluated, right? We want the gradient at that point. Dot with u will give us the rate of change, right? Will give us a scalar, a dot product. So at that point, we can get the gradient, the partial derivatives, as a vector. Dot it with u, that's our directional derivative, remember? Gradient dot u. And that will be the answer to this. Will be the rate of change of w, this output, with respect to heading in this direction. Okay, does that kind of make sense? So I bring all this up because you've got your homework, your written homework has a problem that has the same thing, where you're doing directional derivative for an R4 function or a hypersurface. It's temperature. So it's like you're in a room, and that's R3, and you're going to move around in different directions in the room, and you're finding the rate of change of temperature. So that relates to this. Okay, any questions on that? So that's, if you haven't worked on that problem in the homework yet, you've got that, okay? And then one last thing about this is I want to talk about so here's back to a standard. This is our standard type of directional, or the ones we're used to, directional derivative with a multivariable function of two variables. And I wanted to address this. So we said that there's, so here's our mountain, right? And then the direction we can go are in the horizontal plane, right? So the first thing we had was, what? The angle of, there's like the angle theta, right? And that's, theta was one way to say what direction we want to go and find the derivative in that direction, right? There was that angle theta. And then we had the angle alpha, right? What was the angle alpha that we called alpha? So then say that that's not what I wanted to do. Let's try this. All right, so say this is what? The direction of the gradient. So if that's the direction of the gradient, we said that alpha was the angle, what, between the gradient and the unit vector. Okay, so there's our unit vector, there's the intersection of the gradient. And so then alpha was like this angle. So that was the second angle we talked about, right? So alpha, and to maximize the rate of change, we said alpha should be 0, right? We should choose u to be in the direction of the gradient. And to make a 0 rate of change, alpha should be, what, remember? Pi over 2 or 3 pi over 2, orthogonal to the gradient, right? To make for 0 rate of change. Okay, so there's that angle alpha. Now this is saying if you climb in the direction of the greatest rate of change, at what angle above horizontal will you be climbing initially? So it's asking for an angle. Is that angle theta or alpha? Which is it, theta or alpha? So if this is the direction of max rate of change, say going this way, doesn't look like it how I've drawn it, but for our purposes that's fine. What angle are they talking about? What angle above horizontal will you be climbing initially? Is that alpha or theta? I have a vote for theta. It's a trick question. Is it alpha or theta? Neither, right? It's talking about a third angle. So say that uphill is like this, right? Now it's talking about, according to the rate of change, what's the angle above horizontal that you would encounter? So let's call it beta. That's a third angle, right? So, and that comes from the rate of change, right? So the rate of change is the directional derivative. So we're talking about duf. So how would we get beta from the rate of change? So you have some rate of change of your surface given going in the direction of u. And it's saying, what is the angle above or below horizontal? How would we get that? What's the relationship between rate of change and angle of ascent or angle of descent? You think of it in terms of a triangle. So I have some rate of change. The rate of change is the directional derivative of f. I'm interested in that angle right there. How does the rate of change relate to the angle beta? What's that? Sine of it? Sine is what? Sine is opposite over hypotenuse. Is that what we want? What was that? Why, Harrison? Right. Isn't the rate of change, isn't it how much z changes for a change in your independent, right? So another way to write rate of change according to this triangle would be opposite over adjacent, right? Would be rate of change, right? The ratio of how much z changes to how far you go out. Given any change in this direction, it would be the multiplier. The rate of change would be what you multiply by to get the opposite, how high you go up. Right? Opposite equals m times adjacent. dy equals m dx. That's what we're saying. dy equals m dx. Opposite equals m times adjacent. So the rate of change is like the opposite over adjacent, and that's tangent of beta, right? This is, yeah, so this is like the heart of derivative, right? These questions are getting at the heart of derivative and rate of change. So that's the relationship between that rate of change and beta. The rate of change is the tangent of beta. It's opposite over adjacent. So that's how you can solve for beta, the angle of inclination. Okay. Did you learn something? That's really important, okay? That's really important. Just in general, for calculus, that you have a concept of derivative in terms of how much z changes for a change in horizontal. Okay, any questions on that? All right, so let's start, let's talk about optimization. Optimization per se is not in the exam, but things we're going to use in this are, okay? So, but doing an optimization problem is not part of the exam. It'll be next in the future. So last time we ended up here. We had done this, we find the critical points for this function. And we found critical points at 0, 0, 0, 2, 1, 1, negative 1, 1. And then we used the discriminant, which is kind of like the second derivative test for multivariable functions. To get these values of d, we said when d is positive, you have a max or min, and then to figure out max or min, then you go back and check the second derivatives. And do your second derivative test. And then if d was negative, then that just automatically meant you had a saddle point. So we had two saddle points in this function, 1, 1 and negative 1, 1. And then we had the max at 0, 0, right there in the z-axis, and the min at 0, 2, which was out on the y-axis, right there. So with an optimization problem, you would have a function like this that would be telling you something in the real world, like temperature or distance or volume, given two variables, and you want to find the biggest or smallest value of that variable, right? Biggest or smallest. And so certainly our local max and min are going to be a part of that. But then you also have constraints. You have constraints on your input variables. So it's not that in your real world problem that x and y can just be any real number, right? So x might be some distance or something that's constrained in the real world. Same with y. So given those constraints on x and y, then we want to find out what's the very biggest that your output variable f could be, or very smallest that it could be. So we're just use this problem again to do that, or to do an example. So any questions from last time on critical points, max, min, saddle? Okay, so then we'll go to, so what I want to do now is this, I want the same function, but I want my constraints on x and y to be this. So, so y equals 2x and y equals 0 and x equals 2. So according to this given situation, it only makes sense for combinations of XY ordered pairs that fall in this region. If you're outside of this region for whatever reason, then you have a situation of X and Y that just doesn't make physical sense in the world, okay? So now we want to know, within that region, what's the maximum and minimum values? What's the absolute max and min values of F in the feasible region? That's what an optimization problem is. You have a restriction on X and Y, and so now in combination that gives you a region in the plane. And then so it's like we want to check every one of those points for all those Z values in there, which XY ordered pair gives us the highest Z and which gives us the lowest Z. Okay, but we don't want to check every point because there's an infinite number of points, right? So we want to use the same kind of technique that we did, and we had these problems in Calc 1, where we were doing optimization. So now we're in a higher dimension, right? We're in a higher dimension. So what was it in Calc 1 that we did to find absolute max and min? We said they could occur at one of two places. Do you remember? Right. So either they could occur at the boundary. So now endpoints become edges, right? So before it was the endpoints of an interval. Well, now the analogous situation now is the whole boundary. This is all the edges of, in this case, a triangle. All right, and where else could absolute max or min occur? Critical points, right? Local max or min. So we're still going to have this same approach to finding an absolute max and min. We're going to check what used to be two endpoints. Well, now it's this whole triangular boundary. Okay, and then any critical points that lie inside of the region. So let's graph our critical points here. Let me just turn them on. What were the critical points? Yeah, here we go. 0, 2, was that one of them? There we go. That was our local min. 1, 1. And 0 was one of the saddles. That was our local max. And then the other saddle was over there. Okay. Okay, so here are the points we found last time. So now all we care about, though, for this surface and these critical points are within that. So let's graph these y equals 2x, y equals 0, and x equals 2. And see what, so if I graph y equals 2x, x equals 2, and y equals 0. Stop the madness here. And then look down on the xy plane. Okay, so now, looking down on the xy plane, we see the feasible region is inside y equals 2x, x equals 2, and y equals 0. And so what does this mean for our checking for absolute max and min? So I think this is the point, what, 0, 0, this is 0, 2. This was negative 1, 1. And this is 1, 1. And that's 0, 0. So all we care about is the surface. And that surface extends, it only shows part of the surface. That surface extends infinitely in all xy directions. So this should show all gold in here, right? Should be all gold in there. But in terms of critical points, which ones do we care about? Only 0, 0, and 1, 1 matter, right? These are outside of the feasible region. 0, 2, negative 1, 1 are outside of my feasible region here. So all I'm going to care about for that is 1, 1, and 0, 0. Those are the first two candidates for local max, or absolute max and absolute min, if we didn't know that 1, 1 was a saddle point, right? If we just found that 1, 1 is a critical point, but didn't find it was a saddle point, then it could be an absolute max or min. But knowing that it's a saddle point means that it's not either, right? Because in one direction it's a min, in another direction it's a max. But we'll just include it in the list. Pretend we didn't know it was a saddle, okay? We just got that critical point. It's inside the region, so we'll keep it. Okay, so then what's left is the boundary. So the boundary means I have to check all the points along these three edges. How am I going to do that? Well, I do it one edge at a time. So we got, say, edge A, edge B, and edge C. So I'm going to check edge A, and how am I going to check for absolute max or absolute min on edge A? So we do the boundary. I'll start with A. Y equals 0, right? How am I going to check for absolute max or min at y equals 0? That in itself is an infinite number of points, right? Edge A is still an infinite number of points. How can I find out? Okay, and then? Right, exactly. So we know y equals 0, so we're going to put y equals 0 into the function, and we'll get a one variable function. So we're going to look at f of x comma 0. And f of x comma 0 is going to be 0, 0, minus 3x squared plus 2. Is that right? So now, when y equals 0, I have this curve. Z equals negative 3x squared plus 2. How do I find absolute max or min for that curve? Well, I do it. So I have to treat this as its own little absolute max min problem. And how do we do absolute max min problems? We look at endpoints and critical points. So within this R3 problem of finding what? So we're trying to find the absolute maximum in this region. We know that's going to either occur on the boundary or at a critical point inside. So when we're checking the boundary, each part of the boundary is its own little absolute maximum problem where you have to check the endpoints and the critical points on that boundary. Does that make sense? So what are the endpoints of boundary A? 0, 0, and 0, 2. 0, 0 is already in our list, right? It's already in our list as a corner point here, or as a critical point. That's fine. So how do we find the critical points along there? We're going to take the derivative, right? We're going to take f prime of x is negative 6x. And we want to know where that is. 0, which is x equals 0, which is, again, 0, 0. It's the point we already have. So we're done with boundary A. There is a critical point at 0, 0. We already knew about that one. And the endpoints would be 0, 0, and 0, 2. Yes, 2, 0. Thank you. Is this making sense? Okay, B. So yeah, so I want you to do the same thing for B and C while I take attendance. So for B and C, you do its own little mini absolute max and min problem along boundary B and along boundary C. You're what? You're going to check for each of those. You're going to check endpoints and critical points on the curve that you get from this surface along that boundary. So Chance to talk, get help if you're lost, ask somebody. Where we see an x, right? Make a mistake.
No, you're right.
I have minus 2y last semester. Yeah, it is 2. It's got divided by 3. Is that no solution? Minus
Right, it's 2 squared.
2 squared. So there's a solution. No, it's still no solution. Right?
Yeah. Does it mean there's no critical points there?
There's between the endpoints, there's no critical points, right? We still have endpoints,
Yeah.
which are
2, 0,
2, 0,
2,
2, 4. Two x.
I could be wrong. It's 6 cubed plus 8, yeah. That is 3 squared plus 5 x squared. And then it'd be 14 plus 15. Okay. Right? No. Yeah. Square, which would be 3 times 2x.
Okay, so if you did B correctly, you should have found no critical points in between the endpoints because your quadratic doesn't have a solution. So there's no critical points in between. But you still have the endpoints 2, 0, and 2, 4, the corners there. And then for C, I came up with there was a critical point, 5/7 and 10/7. So somewhere right around there. There's a critical point, 5/7, 10/7. So then, here's our master list. 0, 0, 2, 0, 2, 4, and then 1, 1 with the critical point inside the physical region, and then we only had one critical point here in the 5/7, 10/7. So there are your candidates for absolute max and min. Critical points and boundary points. Yes, please.
Can you explain how you got to the endpoints?
On which one?
Like, all like the endpoints. Like,
Yeah, the endpoints are just the endpoints of each of these boundaries. So this is, the endpoints would be 0, 0, and 2, 0 right there. And then for B, it'd be this one again. You only have to test it once though. 2, 0, and 2, 4. And then for the endpoints of this last one, we already have them. We already have 0, 0, and 2, 4. You don't have to do them twice. But they're just the endpoints of each of the pieces of the boundary. Does that make sense? So it's just those three corners are the endpoints. And then 1, 1 was our critical point inside the region, and then we had a critical point on boundary C, 5/7, 10/7. So you throw those into the function. The biggest Z is your absolute max. The least Z is your absolute min. Make sense?
How did we find one? Just looking at it, or just
No, 1, 1 was from before when we got the critical point that was inside the feasible region. Remember? So all the so the red ones are the critical points of the surface.
Right, so do we?
So you only consider from those. You only consider the ones that are in your feasible region. So there's 1, 1. It's inside.
How did we find the one?
Last class.
Oh.
Last class, we found the 4 critical points of the surface.
Okay.
So do we